Hello students, today we're going to learn about enthalpy, and we're just going to keep talking about energy changes like we've been doing recently. Okay, first of all, let's just go over quickly the things that you know and some things that you're going to learn. You've already learned about endo versus exothermic reactions and chemical processes. We've learned about the law of conservation of energy, different types of energy, and you've also done calorimetry lab and some calculations there. Today we're going to learn about what this word here means, enthalpy, okay? And we're going to learn to do some calculations and apply the meaning of the word. Okay. Again, this is going to be just a very basic introduction into the subject of enthalpy. Okay. Enthalpy basically is just the amount of energy stored within a substance. Okay. This is a very important concept. And we can go deeper into that, but we're just going to keep it at that for now. Okay. Why do we need to study enthalpy? Well, we want to know, okay, the amount of energy that's released or absorbed in a chemical reaction or process. Okay, one common example that you could think of is fuel. Okay, in order for any automobile or airplanes or space shuttles to move, okay, we need fuel that we know can release enough energy to get us from one place to another. Okay, so that's just one basic application, but essentially is we're studying, okay, the changes in energy. Okay, so let's just go a little bit deeper now. Enthalpy, okay, the symbol for enthalpy is H, and most of the time in a chemical reaction or process we talk about delta H, okay, and when we do calorimetry calculations, remember we have the equation Q equals mc delta T, okay, well, the change in the enthalpy, okay, will be just negative Q. So whatever you get here, okay, if you just put a negative sign, that will give you enthalpy. And although this here that I'm going to talk about is not true all the time, we will just consider this for the purposes of this section right here, okay? If the enthalpy is below zero, excuse me, and it's negative, it'll be an exothermic reaction. Okay, if it's above zero, it'll be an endothermic reaction. And when we have the reaction, okay, if we want to calculate the enthalpy per mole, we just get the sum. That's what this symbol here means. That means the sum, okay, of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. And we're going to do some examples to clarify what this means. Okay, let's look at this first problem here. Student performs an experiment by placing 3 grams of magnesium ribbon in a styrofoam cup with 100 milliliters of hydrochloric acid. She calculates the amount of heat released, okay, that's Q, to be 9 kilojoules. What's the enthalpy for this reaction here? Well, remember, okay, this equation here, well, we just got to put negative 9.11 kilojoules. Okay, so there's our first answer right there. That's easy enough. Is the reaction endothermic or exothermic? Well, this number is below zero. Okay, so that's going to mean exothermic. And we call that negative because if you think about it, the system is losing energy to the environment. Okay, the combination here of magnesium and hydrochloric acid is giving off energy. So that's why we call it negative, if it's giving off energy to the environment, which it is. Okay, so that's why that convention right there. Let's do some other problems here. Let me change the color of this so that it's a little bit more readable. I think red will do, or black will do great. Consider the reaction and data table below. Calculate the enthalpy of formation, okay, in this reaction here for ammonium chloride. Okay, so the enthalpy of formation actually is already given to us here in this data table. Okay, what we're going to calculate is the enthalpy here for this reaction. Okay, classify the reaction as endothermic or exothermic. Well, we know the enthalpy of the reaction is going to be the sum of the products. Okay, we only have one product, and here's the enthalpy. Okay, now important to know that this is kilojoules per mole. Okay, this last problem that we did, okay, this amount of kilojoules here was per 3 grams, okay, of magnesium ribbon. Okay, here we're doing per mole of substance, which is what we want. So let's just plug that number in. We've got negative 314.4 kilojoules per mole. Okay, minus the sum of the reactants. Well, we have two reactants, so I'm going to do a parentheses here. We have ammonia, okay, and we have hydrochloric acid. So we're going to do negative 46.190 kilojoules per mole plus negative 167.159 kilojoules per mole. Okay, well, when I solve this problem here, okay, what I'm going to end up with is 101.11 kilojoules per mole. So that's going to be the enthalpy here for this reaction. Okay, so that's our answer right there. Okay, let's do another problem here. There's a little twist to this problem. Okay, we're going to calculate the enthalpy of reaction here for this. Okay, well, we know it's going to be the sum of the products. So we have liquid hydrogen peroxide, which is right here. Okay, so negative 187.8 kilojoules per mole. Okay, minus the sum of the reactants. Well, here we have hydrogen gas in its elemental form, okay, and oxygen. These are diatomic molecules, but it's still just the original element, okay? When it's in the original elemental form, okay, like hydrogen gas, oxygen gas, nitrogen, fluorine, chlorine, bromine, or fluorine, chlorine gas, bromine liquid, okay? Those diatomic molecules, they are going to be, their enthalpy here is going to be 0 because that's the starting point, so to speak. Okay, so any element that you see in its element form, its original form, the enthalpy is 0. Okay, so since this is minus 0, negative 187.8 is going to be the enthalpy for this reaction. Okay, and all of these numbers here were calculated experimentally from starting off with the basic elements and then making these products. Okay, so this is how we know these numbers here. Okay, so again, if it's in element form, we consider it to be 0. Let's do this last one here, and there's one more little twist. Okay, so we're going to get the sum of the enthalpy of formation for the products. Well, I have 2 gaseous water molecules and 2 gaseous sulfur dioxide molecules. Since this is per mole, okay, I need to multiply whatever number I'm using by the number of moles in the reaction. So I'm going to do here 2 moles of the enthalpy for gaseous water, which is going to be negative 241.818 kilojoules per mole. And then we're going to add because it's the sum. And then I also have 2, okay, of sulfur dioxide. So I'm going to do 2. And this is going to be a big number. I'm going to try to squeeze this in here. Okay, I did it, sort of. Okay, and I'm going to close my brackets. And then I'm going to subtract that from the sum of the reactants. Okay, well, I have 2 hydrosulfuric acid molecules, so I'm going to do 2 hydrosulfuric acid gaseous state. There it is. 2 times negative 20.63 kilojoules per mole. Okay, and again, we're multiplying by 2 because this is per 1 mole, and we have 2 moles in this reaction. Plus, I have 3 moles of oxygen, but remember, this is in its element form. Okay, there's just one type of element there. So we're going to call that 0. Okay, and then I'm going to close those brackets. And then once I do all that math, okay, the number that I come out with is this right here. Okay, so that will be oops, this is supposed to be a negative number. Okay, that'll be the enthalpy of reaction. And of course, this is exothermic because it's negative. This is also exothermic. And this here, okay, is exothermic as well. Okay, so that was just a little introduction. We did 4 simple problems, okay, regarding just enthalpy of reactions.